Let's talk about kinetic energy and the work kinetic energy theorem. We've talked about kinetic energy. We've defined it previously also. Kinetic energy is the energy due to the motion of an object, and the equation for our discussion is always going to be half mv squared. Potential energy can be different equations depending on the force you're dealing with, but kinetic energy is always half mv squared. Again, it's the energy due to the motion of an object. Now let's answer a question related to kinetic energy. There is a ball that has half the mass and 8 times the kinetic energy of ball B. What is the ratio of the speeds of the two balls, V8 divided by VB? Pause the video, think about, well, you should write down in this case, you won't be able to guess. So pause the video and work on it. Okay, so the answer is 4, and let's see why that's the case. So what is given to you is that MA, right, ball A has half the mass, which means that its mass is half. So if B is 10 kilograms, let's say MA is going to be half, which is 5, so you have to divide that by 2. And kinetic energy of A, sorry, is 8 times the kinetic energy of B, right? So Ka is 8 times Kb. So how do you solve this now? So we know that now Ka is going to be half MA VA squared is equal to 8 times half of MB VB squared, right? So then how this if you want, you can solve it any way you want, but this half cancels out, and you get I'm going to plug MA is MB by 2 and VA squared. Okay, and 8 times MB times VB squared. Now the MB cancels out from both sides. The 2 multiplies, if you multiply 2 on both sides, this becomes 16. So we want VA divided by VB. You take the square root, you get VA divided by, I'm running out of space, let's do it over. So VA divided by VB is going to be, if you take the square root of that, you get, so VA squared divided by VB squared is going to be 16. So VA divided by VB is going to be 4. Okay, so this is why this is the answer. Okay, let's answer another question. So this is related to work, right? So in this case, you have a crane that lowers a girder, and it's being lowered at constant speed. There's work done by gravity and the work done by tension. Which one of these is true? Which one of these is positive, negative, or 0, or both are 0? Think about it, and it's constant speed. Pause the video and think about it. Okay, so the answer is B. Now in this case, what's going on is that the object is being lowered. So let's say this is the object, right? Force of gravity is down, tension is up, right? Now, one of the from my experience, one of the issues that you have is that, okay, if it's constant speed, then the total the total work done might be 0, right? But that's not the case. You see that the total work done is going to be 0 in this case, but the thing is that it's being the work done by individual forces, right, can be non-zero even though the total work is 0. So some of the students have seen that answer this. Obviously this is not right, because there's obviously work being done, and since the crane is being lowered, right, force of gravity is in the direction of displacement, so work done by gravity is positive. Force of tension is in the opposite direction to displacement, so this is your displacement, and therefore the work done by tension is negative. Okay, so the work kinetic energy theorem states that if you have a situation where where there are multiple forces acting on an object, you find the total work done, and that total work done is equal to the change in kinetic energy of that object. So that's why so this is where that misconception, going back to the previous question, that if you have a constant speed, the change in kinetic energy is zero. So the work done by individual forces is zero. So that's not true. The work done by individual forces can be non-zero, but they add up to give you a zero. The total work would be zero. But in any case, if there is a change in kinetic energy, the total work would be non-zero. And that's where the work kinetic energy theorem is useful. That you have multiple forces acting on an object, you find their total work, and then just set that equal to half the change in kinetic energy. Now let's look at an example that demonstrates work kinetic energy theorem. So you have two people pushing on a bobsled. It starts from rest, and then they move it at a distance of 50 meters, and the net force they're applying throughout the motion is that distance is 270 newtons. Now we're going to neglect friction. What is the sled's speed at the end of 50 meters? So you have to use the work kinetic energy theorem to find the speed of the sled after it has moved a distance of 50 meters with this force being applied. Right. So the quantities that are given obviously are the mass, the force that's being applied, the distance, and that the initial velocity is zero. So we can use the work kinetic energy theorem. We can find the total work that done by these two people that are applying this constant force, and we can find the distance that the final velocity after the sled has been moved by a distance of 50 meters. So what kinetic energy theorem says that change in kinetic energy is equal to total work done. So change in kinetic energy is therefore equal to initial kinetic energy plus the total work done. And so half mv final squared is equal to half mv initial squared. So this is the work done by the constant force. It's just force times distance, because there's usually a cosine theta, which is 1 in this case, because force and distance displacement are in the same direction, the theta equals 0. So v initial is 0, so you're just left with half mv squared equals force times distance. You rearrange the equation, you get this, and when you plug in the numbers, it's 8.3 meters per second. So that's the velocity at the end of that displacement of 50 meters. So let's look at a question. In this question, you have different boxes that are pulled a distance of 10 meters across a frictionless floor. Which box experiences the greatest change in kinetic energy? So which one experienced the greatest delta K, the greatest change in kinetic energy? Pause the video, think about an answer. Okay, so the answer is D. Now, so notice that, so what you have to think about is total work done. Work done is equal to the change in kinetic energy, right? And work done is just F times D, right? Now, the greatest change in kinetic energy is going to be where F times D is the greatest for each of them. So you just have to, since D is the same, right? It's just 10 meters for all of them. You have to just pick the one with the greatest force. There you go, 20 newtons, right? So that's again a usefulness of the work kinetic energy theorem, that it connects the change in kinetic energy with the work done. So in this case, since the displacements were the same, you just think about the one with the maximum force being applied. Okay. Now let's look at this example. Again, demonstrates the work kinetic energy theorem. In this case, we have a skier gliding at 2 meters per second when he starts down a slope. So initially he's moving at this speed, right? And then he starts down a slippery slope, which is 50 meters long, and the slope is 10 degrees. What is his speed at the bottom, right? So this is his initial speed. Now, again, we're going to use the work kinetic energy theorem. And so the forces that are acting on the skier are the normal force and force of gravity. We're, again, assuming that it's frictionless. The quantities that are given are you can choose your own axis where whatever the skier starts, you can choose that as the origin. Initial velocity is 2 meters per second. Mass is 70 kilograms. Now the displacement x1 minus x naught is going to be 50 meters, and you have to find the final velocity. Now in this case, you can approach this problem a few ways, but one way, which is done over here, is that so since work is force times displacement times the cosine of the angle, so this is your force of gravity. Work done by normal force is going to be 0, right? Work done by gravity is going to be force of gravity times the. So now this is okay. Let's look at this. So this is the skier, right? Gravity is down over here, right? Now, since we talked about this in the previous chapter, if this whatever this angle is going to be the same as that. So this is also going to be theta, which means that they both are 10 degrees, right? So now this is your force of gravity. This is your displacement, right? So this angle is going to be 90 minus theta, right? 90 minus theta, right? So that's what is meant over here. So this angle, right? This angle alpha is 90 minus theta. Since this is 10 degrees, the alpha is going to be 90 minus alpha, which is 80 degrees. So you just have to multiply the force of gravity times the displacement times the cosine of 80 degrees, and the displacement is given as 50 meters, right? The force of gravity is mg. This is mass. This is 9.8. And cosine of 80 degrees, that gives you this answer. Now we found the work done by gravity. Again, the work done by normal force is 0. There's no friction, so gravity is the only force we have to worry about in order to find the work done. Now from the work kinetic energy theorem, we know that the total work done is going to be equal to change in kinetic energy. Now we have found the work done, so we know what W is. We know the initial velocity is 2 meters per second. We have to find V1, so it's all about rearranging the equation. You divide both sides by m, multiply 2 over, and then plug in numbers. You get 13 meters per second. Okay, so that was another example that demonstrates the work kinetic energy theorem. In the next video, we'll talk about the work done by a variable force. So that was it for the. So we've been talking about constant forces. So we'll talk about variable forces in the next video.